Okay, the purpose of this video lesson is to kind of explain to you the heart conduction system and an ECG, EKG, the whole thing you've maybe seen on a medical program, where they're measuring the heart and seeing if it's beating. And when it stops beating and they pull out the paddles and they electroshock something, which actually doesn't necessarily work that way. Usually the paddles are used to put it back in rhythm. So this is a normal rhythm. We'll talk about that a little bit. So yeah, you do have a set of handouts, and I would encourage you to kind of add to that as we go through. So let's begin. Now this slide will look slightly different on mine. If you want to hit pause and write these terms down or do it as I go along, I'm going to kind of do it in a different order. I didn't number them very well. So I'm going to start kind of the beginning of the conduction and go to the end. So we know the heart is a muscle and it needs electrical stimulus to beat. However, it is very much independent. It does not rely on the brain to send a message for every heartbeat. It has an automatic pacemaker, so to speak, built in. And some of you will know somebody who has a pacemaker. You may have had a relative or even children have to have pacemakers because their heart doesn't quite beat normally from a younger age. And so we'll talk about that cycle a little bit. So I'm going to start up here with number one. This is called the SA, or the Sinoatrial Node. Let me grab a color here. I'm going to do blue. That'll probably stand out. So the Sinoatrial Node is a bundle of heart muscle. It's necessarily wouldn't say it's nervous tissue, but it's specialized heart tissue that will regulate heartbeat. This is the natural pacemaker, and it is located just kind of in the wall of the right atria. So you've got the superior vena cava dumping in here and the inferior vena cava dumping in here. So it's in the wall of that atrial muscle that we saw when we did the deer heart, if we did a deer heart the year you're watching this. So that's this SA node, or the sinoatrial node. Next, so once that kind of contracts, once it sends an electrical stimulus, it will travel through some other specialized pathways, and one place it makes it over to is the left atria. And this little bundle here is called Bachmann's bundle. And Bachmann was the scientist who kind of discovered this. And this will, so once the SA node, sinoatrial, and once the message gets sent out here to the Bachmanns, that's going to cause the atria to contract, which is going to sort of push the blood down into those lower ventricles. So this Bachmann's bundle. And that actually isn't labeled on your diagram when you go to color 105. Just be aware of that. There is a specialized network of fibers that run underneath the aortic arch along into the left atria. All right, so that electrical message then makes it down to this little bundle of specialized fibers, and it's very small. I think I read it's somewhere around 3.5 millimeters by 1 millimeter. So it is a very tiny little bundle of specialized muscle that is called the AV node, or the atrioventricular node. Now, I'm okay with you abbreviating these things as long as you do know what those things stand for. So even if you're doing a Quizlet or something like that and it says sinoatrial and you've just put SA node, that's fine. Just make sure you're ready on a test or an assessment that if I put the SA node is the what, make sure you do know that those terms, sinoatrial or atrioventricular, much like we had those AV node or AV valves. So this little bundle, the AV node, is sort of another collection of small bundles of specialized muscle that will then collect the message and send it back out. So this is getting the electrical signal from the SA node. It receives that message and then sends that message out all at one time to begin the beating of the bottom chambers, the ventricles. This little segment right here that I'm going to shade in blue is called the bundle of His, or sometimes it's called the His bundle. His was the last name of the scientist who discovered this, and we got a lot of scientist names here. They like to name things after themselves when they, or at least in retrospect, looking back, whoever finally settled the name. So the bundle of His, or the His bundle, is just the road, the network of fibers, muscle cells that the message sends, that travels down to this interventricular septum. Then it's going to branch into the right and left bundle branches, and so you see those bundle branches kind of curve around the wall of the ventricles. Eventually, it makes it into these smaller little fibers that are all embedded within the muscle tissue. They're called Purkinje plexus. Purkinje plexus. Purkinje, another scientist name. Plexus is just the idea that they are a network of these fibers that are embedded in the tissue. Because really what we want to have happen is we want all of this to contract simultaneously. And that is the goal. And so now it may not be down to the nanosecond exactly the same, but it is close enough that whenever the message goes through the Purkinje plexus on both sides, and so we've got right Purkinje plexus and left Purkinje plexus, that these ventricles are going to contract simultaneously. And that's really what we want, to push blood either up into the pulmonary trunk or up into the aortic arch into the rest of the body. So hopefully that helps with the cycle, and I'll go through it one time really quickly here. So we've got the SA node. That message will get sent out over here to the Bachman's bundle. And again, this is just the message is traveling along here so that the atria will contract simultaneously. Then that message gets received here to the AV node, atrioventricular node. It will then stimulate, it will activate, it will what's called polarize, and it will send the message down the bundle of His, the His bundle. That will be diverted into two different bundles, the left bundle branch and the right bundle branch. That gets to smaller and smaller fibers, the Purkinje plexus. And when it reaches the end of those, it'll get to a certain strength of signal, and the muscles will all contract simultaneously. And then, in fact, when the message stops, they will relax and they'll repolarize what's said. They will relax, reloading them for the next conduction cycle. So hopefully that helps with the anatomy of this plate 105. And you have the option of coloring this 105, and you'll be coloring. I don't know whether you need to for this. There aren't that many terms, but if you find that beneficial, then please do that. So next, let's talk about the ECG or EKG. And so our books, it's ECG because it stands for electrocardiogram. So it's measuring the electricity that's going through the heart, because we do control muscle contractions through electrochemical messages. So we're measuring that when you see this, it's a graph. The y-axis is the voltage that's traveling or that's being collected, and time. So it is a time graph. This is over time. So it will continue and continue. And so if you've seen those programs on TV that are medical programs, you'll see that's kind of going across the machine. But then this can actually be printed off in paper form. And so I want to talk about just the anatomy, so to speak, of this. And it does repeat. So you're going to notice this A is over here. So once it goes through one cycle, so I guess you could consider kind of like this over to like right here is one cardiac cycle. So that's going to be one time through that entire conduction system. And so in the last image, we talked about the cardiac cycle. This is what we'll see as the electricity as it travels through all those different nodes and segments and His bundles and things like that. All right, so basic anatomy. This first wave is so I've got it labeled A here, is called the P wave. Now, why these numbers or why these letters were come up with, I honestly don't know. It doesn't really correspond to, it's just letters in the alphabet. So this first wave is the P wave. Then the next wave that we have here, and I'm going to skip over D, E, and F for just a moment. So this next thing that we have is called the QRS complex. QRS complex. And it's a complex because there's actually a little dip in the voltage, and then the R, it goes way up. So like this is kind of like the R wave, and then it kind of goes way down again. And that has to do with the polarization and repolarization of the muscle. So QRS complex, that's the big one that when you're measuring your pulse, this is kind of what you're feeling here in a way. You're feeling this QRS. This is the big push of the heart. Then letter C here is going to be what we refer to as the T wave. The T wave. Okay. Then it begins again, and we'll have the P here again. Then just off the page here, this would continue up, and that would be the next QRS complex. So it goes the P wave, the QRS, and then the T. So we're just looking at these three significant waves. Then these other segments in between, looks like there's really nothing happening, and that's not necessarily true that nothing's happening, but this is wherever there's no electricity. So this is kind of in between different events. So we actually call this segment right here between the P and the Q where this begins. We actually do call that the PQ segment. It's just a measurement of time, and I'll talk about what that time might mean a little bit. Then over here, we're going to have the ST segment. So it's the time between the S, this D, this lower polarity, this lower voltage, and when the T wave begins. Then over here, what would you think we're going to call this little segment of time between here? And if you said the TP, you are correct. So we don't go PT because that would just be weird, because that would be the time from all the way over here, all the way over here. So we do actually say the TP segment. It is the time between this T wave, where it kind of goes back to normal whenever the wave of electricity has stopped, to when the next P wave begins. Now, I will come back and talk a little bit about what those segments of time mean once we talk about what happens in the P, what happens in the QRS, and what happens in the T. And really, it's pretty straightforward. We have 4 events that are going to be happening. So I'm going to actually go back to this guy up here. And so we had, so let me grab, and so you don't necessarily have this, but this is kind of those 2 diagrams together. So I should have wrote this in but better. And here's the T. And then we'd have, again, we grab red here to kind of do the next P there. So we've got the next P wave that would be beginning. So this is all about the electricity that's going through these different nodes and whatnot, but we also want to think about that electricity causes certain things to happen. And it either is going to cause the muscle to contract, or it's when the muscle is relaxed. So what happens in the P wave, we're actually going to start right up here. So the P wave is actually, because this electricity actually kind of builds up and it gets to a certain level, and that then triggers the muscle to contract. So this first thing that's actually going to be happening is whenever the atria are contracting. So I'm going to put A for atria. The atria are contracting. So I'm going to put A/C. So the atria have contracted. That electrical signal then makes it down here to the AV node. This next thing, what this is going to be, is this going to be the ventricles that are then contracting. So the electrical signal builds up to a certain level, and that message gets sent all the way down the bundles and to the Purkinje plexus, and that's then going to cause the ventricles to contract. And again, I would probably put a few more words here. It's just hard for me to necessarily write those things out. At the same time that this is happening, we can't really necessarily see this, but at the same time, the atria would be, and I'm going to put R for relax. So that in the P wave, go back, P wave, the electricity is going to build up, it contracts. Then that message continues down to the AV node. The electricity will build up to a certain level. The ventricles will then contract. At the same time, essentially, the atria are relaxing. So as the bottom chamber squeeze, the atria are relaxing. And they have to relax so they can be actually filled back up with blood, and we'll kind of see that in the next slide. Now T, what would you guess is going to happen in the T wave? If you said the ventricles are going to relax, you are correct. So at this point, this is when there is actually enough electrical message, and this is a big enough muscle that it actually does have to do some work to relax, to open back up, so to speak. And so that's what's going to happen in this T wave. The electricity will build up enough to actually then, instead of going from the squeezed, it'll go into the relaxed, or the contracted is the squeezed. Then it all starts again. Then the P wave will contract, or will cause the atria to contract, and the whole thing then begins again. Okay, so you also have, so hopefully that kind of explains what's happening inside of that. Now, these different segments we had, so we had the PQ segment. Well, that just really represents the amount of time between the atria and ventricles contracting. So it's just a time period between these events. And this next segment we called the ST segment is the time between the ventricles contracting and the ventricles relaxing. So they're the amount of time those ventricles stay squeezed. Then we had that TP wave. That's just the time between the ventricles relaxing and the atria contracting again. Now, why are these time periods important? Well, if you have a heart event, or if you have an irregular heartbeat, or if you have something that's not quite right, you may have what's called a blockage. And what that blockage means is perhaps this time is just a little too long, or maybe it's a lot too long. And so a doctor, a cardiologist, would read your ECG, your EKG. It's sometimes called a K because in Britain, cardio can have a K. So if these times are longer, it just means there's something blocking that signal getting to where it needs to go. And so depending upon how long that is will determine maybe the severity of the heart damage, because remember, these are heart tissues, and so they may have to go in, and different things can be done for different events. But I just want you to be aware of that those different segments represent the time between the events. And so once you have what these things represent, the P, the QRS, the T, what they represent, then you can just know that segment is the period of time between those things happening. And it can be longer than it should be, and that's sort of what we might call a blockage. Different kind of blockage than like if you have an artery blockage, a little different term. Just means that something is keeping that signal from getting to where it needs to go as quick as possible. So sort of like if there's I don't know, a road closure, it's going to keep you from getting to school quick enough. And so there's a blockage of the road, so to speak, that keeps you from going, or if you have to slow down because the speed limit lowers, maybe that's kind of another analogy you could think of. All right, now you will also have, and I'll probably include this, I think I'll probably print this off. Oh, actually, no, I did. So this diagram is another way of kind of showing what happens during different stages. So, and I wish it was a little bit better color, but this first one they're doing is the P. And so this goes along right here. And so this is showing you that the atria is contracted. Now, they give you a word here called systole. Systole is whenever the muscle is contracted. Think systole, think squeezed. Systole, squeezed. So here's that P wave. Then we're going to have the time between its contracting and whenever the next portion of what's happening. So now we have this QRS. The QRS is going to be the time that the ventricles begin to contract. And so now the ventricles are in systole. Now, as it turns out, at the same time, the atria would be relaxing because that all happened during that QRS. So, and it kind of explains what's happening here. There's a first phase, then a second phase. So this is, they call it ventricular ejection. So this is whenever it finally squeezes enough to push the blood out either the pulmonary trunk or the aorta, which interestingly enough, they've kind of got crisscrossed. But anyhow, so that's the QRS, a lot of things happening. So this is that ventricle systole. The ventricles are squeezed. The atria have actually made it back into what's called diastole. And so you see here, so it's this inner circle is labeled atrial diastole. From here all the way around, okay, the atria is relaxed. It's opened up. Next, we're going to read into the T wave. And the T wave is showing when these muscles are relaxed again. These muscles relax again. And as they relax, the blood is going to flow back into the atria. So they're being refilled. So here we show the atrial and at the same kind of time, that blood will actually start flowing down into the ventricles. Then finally, once it goes into systole, the rest of the blood kind of gets pushed. So the blood does kind of go down into those valves through the valves, as long as the ventricles aren't contracting. Any blood flowing back into the atria can, just because of gravity, flow back down into these ventricles. But I do want you to be aware of these terms. Systole for squeezing, that's whenever they're under higher pressure. So systole is squeeze, diastole is relaxed. And this is probably the best time, or is a good time, to then talk a little bit about blood pressure. Because blood pressure is a direct relation to the ventricles, only the ventricles, contracting and relaxing. So you've been told, let's suppose that you are told that your blood pressure is, you go measure blood pressure, it's 135 over 90. What do these mean? Well, these are actually millimeters of mercury. Millimeters of mercury, and that's probably going to go off the screen. But it's a pressure. And this is also millimeters of mercury. Long time ago, when our devices would actually kind of push against mercury and see how far it raised it up. And so it would raise it up 135 millimeters, would kind of push the mercury up. That's where that comes from. But for us, let's just note these are pressures. So this 135 is the big push. This is when the ventricles are contracting. That corresponds to systolic, or the systole, whenever the ventricle is contracted. The 90 is the diastolic pressure. This is the pressure in your blood vessels when they're between ventricles contracting. So this is when your ventricles are relaxed. So this is sort of like the pressure whenever it's not being pushed forward. And it has to be lower. It just does. So that's this pressure down here. So this person who we've said is 135 over 90, what does that actually mean? Well, if we take 135, and so I'm going to say it's about right here, and bottom pressure was 90, if we come up and we figure out where that kind of fits in this orange, it's right here. So that person they have pre-high blood pressure, and this is resting. So obviously when you're exercising, you're doing different things, your blood pressure is going to change. But this is a resting blood pressure, not taken in the morning, perhaps not at night. This is just kind of during the day, because in the morning, your blood pressure actually always tends to be a little bit higher. So it's here. So this person is just on the verge of high blood pressure. Now, there are a bazillion of these charts out there, and every chart can be actually slightly different. And there can be different levels. So there can be pre-high blood pressure, then there's level 1, level 2, level 3, different severities of blood pressure. So this I just picked because of its simplicity. When we say you're told that your blood pressure normal is 120 over 80. And so that actually puts it right here. So that's actually the top of the normal level, although nobody's going to get too worried. If your blood pressure is normally 125 over 83, so it's right here, I don't think anybody's going to get too concerned. That is pretty healthy blood pressure. And you can actually have too low blood pressure, and this just means your heart isn't quite working hard enough. So this, I just want to give an overview and kind of talk about what those numbers mean and give you another indication. The systolic, that's the squeezing. That's whenever the ventricles are contracted, and diastolic whenever they are relaxed. So next time you have your blood pressure measured, or you have a relative who they said their blood pressure is, their blood pressure is 180 over 100, and you're like, holy moly, that was way up here in this red off the chart. Well, this chart actually goes a lot higher. There are blood pressures I think 230 is the highest I've ever seen on a blood pressure chart, and that is pretty high blood pressure. That is twice the pressure, and a lot of times it's not because your ventricles are squeezing too hard. It's because your 8 arteries, remember arteries can contract, your arteries are actually squeezed. The blood vessels or the smooth muscle in the artery is squeezed, so the blood's got to be pushed harder. There has to be a higher blood pressure to get the same amount of blood through. And that's why blood pressure medications don't necessarily work on the heart. They're working on the blood vessels to open those up a little bit. So hopefully you found this informative and you kind of understand the heart cardiac cycle a little bit better. I would now encourage you to go off and do the purpose games, color the diagram, do the Quizlet to better understand the heart. So thanks for watching. And if you need to go back and watch any part of this, please do. Thanks.